All right, so let's talk about examples of centripetal force next. So let's imagine that you are at Berlin Raceway and you are watching Shako race, okay? So Berlin Raceway is somewhat of an oval. It's a little more circular than it is oval like the Indianapolis Speedway. But anyway, I'm gonna kind of draw it out so it looks a little more oval. So when you have an oval, basically you have two circles that are in an oval. So here would be one of the circles, and here would be two of the circles, or the second circle, and each of them has their center point, okay? All right, now, if you are at Berlin Raceway and you are watching the race, and there's an oval racetrack, Shako's no dummy. He knows how to race on the racetrack. He knows that you want to be on the inside when you're taking a curve. He knows that you want to be on the outside when you're on the straightaway. And he also knows about speeding up and slowing down at the appropriate times. So let's suppose that he is coming around one of these curves. Now remember, there are two vectors that are happening at the same time. There is a vector that wants to go in a straight line, and there's a vector that is pulling Shako to the center of the circle. Now, ideally, we want this force that's pulling him to the center to be a little bit stronger so he stays on the curve, okay? Because the minute that that's not strong enough, then this guy is gonna win, and the car would go off of the racetrack. Now, Shako takes the inside of the curve, and he forces one of his opponents to go out here on the outside of the curve. Now, what's gonna happen? The guy on the outside of the curve could possibly, and I have seen it happen at Berlin Raceway, funnier than heck, well, probably not for the driver, but funnier than heck as a person sitting in the audience. There is a force that is pulling the object to the center, and there's a force that is making the object go straight. Remember, the one that wants it to go straight, obeying Newton's first law at a constant speed, is that horizontal vector. The one that's pulling it to the center is the vertical vector. That's the one that's changing its direction, accelerating, following Newton's second law, F equals ma. Now, if Shako can get his opponent to be on the outside of the track, and if he's going too fast, what will happen is the straightaway arrow will win, and the arrow pulling towards the center of the circle won't be strong enough to keep him on the circle. So while Shako is curving and going around the curve, his opponent, who ended up on the outside of the track, could end up going straight off of the track, over the hill, through all of the dust, and not be on the racetrack anymore and not be part of the race. It's actually quite hilarious when it happens. Now, remember that there's a centripetal force that's pulling towards the center. Why is that happening? Because that object is changing directions. It's changing directions because there are two vectors that are happening. So when you are doing your project, you're going to pick up a demonstration, and in that demonstration, something is going to be going on some sort of curved path or circular motion. You're going to have to talk about that horizontal vector for me, and the fact that it's going at a constant speed, obeying Newton's first law, and it wants to keep going in a straight line. You're going to talk to me about that vertical vector. The vertical vector is the vector that's pulling the object towards the center, and it's accelerating because it's changing direction. Because it's accelerating, it's obeying Newton's second law, F equals ma. The two are working in conjunction, which is what makes the curved path. The minute that one outweighs the other, then we've got an issue going on. So here is a second example of something that is traveling in a circular motion. So normally, if we were at school, we would go over to the West Elementary playground, and we would actually play on the merry-go-round on the playground. Now, the merry-go-round, when I was a kid, they stopped letting people go on the merry-go-round because here's what would happen. kids would get on and they would spin and spin and spin and spin, and they would get going so fast that that centripetal force pulling towards the center seeking force, that particular vector wasn't strong enough. So what would happen is the vector that was horizontal, that was going in a straight line at a constant speed, would be the winner. And kids would go flying off of the merry-go-round. Now, as a person who was on the merry-go-round and didn't fly off, I would always chuckle at the person who did. Well, what would happen is those kids would fly off and then break their arm or something like that. And so the ride was deemed unsafe. And so then the rest of us couldn't ride. And it just didn't seem fair to me. Again, you are going around and around and around in a circle. There is a vector that is going horizontal that wants you to go straight according to Newton's first law at a constant motion, constant speed. There's a second vector that is pulling you towards the center. It is a center-seeking force, and it's accelerating because of a change in direction. So as you do your demonstrations, you're going to want to explain the fact that there's a horizontal vector, Newton's first law, constant speed. There's a vertical vector, a vector that's pulling towards the center, and it's obeying Newton's second law because it's accelerating due to a change in direction. And then you're going to tell me that there's some kind of a center-seeking force that is keeping that object going in a circle. Good luck.